Hi, my name is Seok Ki Moon, and I'm BRU21 PhD candidate. Within BRU21, I'm working on the area of the field development and economics. My research topic is improved planning methods for more energy efficient and environmentally friendly field development. And this project is sponsored by Aker BP. The purpose of the field development is to maximize the value of the field. Here, the value of the field means the economic value in most cases. But these days, the value of field does not only mean the economic values, but also means the greenhouse gas emissions and energy efficiencies. To increase the value of the field, the early phase field development planning is very important because it is the design phase where most of the important design features are determined, and also it influences on overall project values. But the current field design procedures tend to consider only economic values, not the greenhouse gas emissions and energy efficiencies, which are becoming more and more important these days. So my research objective is to improve the early phase field development planning method by considering greenhouse gas emissions and energy efficiencies of the field. There are several greenhouse gas emission sources in the offshore field, and among them, the gas turbine is the largest emission sources when generating power from the offshore installations. The gas turbine accounts for approximately 85% of the greenhouse gas emissions in the offshore field. So we can expect a significant greenhouse gas emission reduction by only changing the power supply method of the offshore field installation. So to reduce the greenhouse gas emissions, there are two measures that has been proposed. One is electrification, and the other one is to increase energy efficiencies. The electrification means that the offshore installations are powered by the electricity, not by the gas turbines. There are two proposed concepts for the electrification. One is using the offshore wind farm, and the other one is the power from shore. In case of the offshore wind farm, we supply power of the offshore installation by using the renewable energy source. And in case of the power from shore, we supply power by connecting offshore installations to the national grid via subsea power cable. Increasing energy efficiencies of the gas turbines can be another option to reduce the greenhouse gas emissions of the offshore field. Combined cycle gas turbine can be a good example. The main principle of the combined cycle gas turbine is to use the waste heat from the combustion process to generate the additional electricity. In this way, the energy efficiency can be increased approximately from the 35% to the over 50%. To compare with the normal gas turbines, the combined cycle gas turbines uses less fuel gases to generate same amount of the power, meaning that it emits less greenhouse gas emission to the air. Then, how can we evaluate these options in the early phase field development plannings? Let's take a look at the simple case studies. Suppose that there is an offshore oil field that we want to develop. The water depth of the field is very deep as 1,200 meters, and the existing infrastructures are far located, and there are even no infrastructures for the oil transportation. Then the basic development concept will become like this. Because of the water depth, floating vessel with subsea development can be a possible option for development. Shuttle tanker for oil transportation is preferred due to the lack of infrastructure. Since it is a tight reservoir, we can think of gas injection to support reservoir pressure, and multilateral drilling can be a good option to increase productivity and to reduce the cost. Then the subsea field architectures can be designed depending on the number of producers and injectors. On the floating vessel, basically 3 types of the surface process is required to stabilize crude oil, gas compression, and produce water treatment. The surface process is important because the power demand of the entire field is determined based on the surface process configuration. It may have heaters and several numbers of compressors and pumps. Based on this, we can now move on to the power supply method. Here, there are 4 types of the power supply method, as I mentioned before. And to evaluate field development alternatives in the early design phase, we can make a value chain model encompassing every field development options mentioned in the case study. Here is a schematics of how value chain model is created. It starts from the reservoir, well, and then integrated into the production network. Then, the production network model is combined with the surface process model to see the field production performance, like production and injection profiles, and so on. Then, this becomes the basis of the economic calculations, like net present value and break-even oil prices. But if we consider the greenhouse gas emissions and the energy efficiencies, this is not enough. One way to estimate the field greenhouse gas emissions and energy efficiencies is to include power supply options in the value chain model. For gas turbine options, we can add gas turbine model into the value chain model. And for power from shore and offshore wind farm options, we can consider the capital cost of each options in the economic calculation depending on the power demand. So first, we estimate the field power demand from the integrated production model. Then the field power demand is taken as an input to the gas turbine model such that we can estimate the amount of the greenhouse gas emissions and the energy efficiencies of the field. We can then calculate the emission intensity and energy intensity of the field, which will help to support decision making. In the economic calculation, we also consider CO2 tax to investigate the influence of each power supply options on the field development. Here are some of the key results from this study. The left-hand side figure shows the carbon emission intensity and energy intensity of the field. These indicators mean the amount of carbon emissions and the amount of energy required per produced barrel oil equivalent depending on the production scenarios. These indicators can be useful environmental information when planning the field. Another figure shows the break-even CO2 tax required for field development concept conversion from the gas turbines to the power from shore and wind farm for this case study. This enables field planners to investigate the effect of the CO2 tax on selecting field development alternatives during the decision-making process. We can also simulate the future CO2 tax scenarios during the production. The major benefit of using this method is that field planners can still find an economically profitable field development solutions with low carbon emissions and higher energy efficiencies. You can find more details about the result in this paper. And thank you for your attention.